In this lesson, we'll take a look at the essential components that make up a CPU and how they work together to carry out instructions. We'll also explore the von Neumann architecture, which is the basic design that most modern computers are built upon. The central processing unit, or CPU, is at the heart of a computer system. Its main job is to execute instructions and perform calculations on data. The CPU does this through a series of steps called the Fetch-Execute Cycle, where it fetches instructions from memory, figures out what they mean, and then carries them out. The Fetch-Execute Cycle is the process that the CPU goes through to retrieve instructions from memory, figure out what they mean, and then carry out the specified operations. The cycle has four main stages: fetch, decode, execute, and store. First, the CPU fetches the next instruction from memory. It uses a special component called a program counter to keep track of where the next instruction is located in memory. Once the instruction is fetched, the CPU's control unit decodes it to understand what operation it represents and what data it needs. Then, in the execute stage, the CPU actually carries out the operation specified by the instruction. It uses data from the registers or memory, depending on what the instruction requires. If the instruction changes any data, the results are then stored back into memory or registers, based on the specific operation. The CPU repeats this fetch-execute cycle over and over and over again, allowing it to execute a series of instructions and make the computer perform various tasks. Now let's take a closer look at the main components that make up a CPU and what they do during the fetch-execute cycle. Let's start with the Arithmetic Logic Unit, or ALU. The ALU is like the maths whiz of the CPU. It's in charge of doing all the arithmetic, like addition and subtraction, as well as logical operations, like AND and OR on data, which we'll get onto in later lessons. During the execute stage of the fetch-execute cycle, the ALU takes in data from registers and performs the operation that the instruction tells it to do. The control unit is like the boss of the fetch-execute cycle. It's responsible for coordinating everything and making sure the cycle runs smoothly. During the fetch stage, the control unit retrieves the instruction from memory using the program counter and sends it to the instruction register to be decoded. It then controls how data and signals flow between different parts of the CPU to make sure that the instructions are executed properly. Cache is like a small, super fast memory that's built into the CPU. It stores data and instructions that are used often so that the CPU can access them quickly. During the fetch-execute cycle, the CPU always checks the cache first. If it finds the data it needs in the cache, called a cache hit, it can grab it much faster than getting it from the main memory or RAM. Registers are like tiny high-speed storage units inside the CPU that hold data temporarily during the fetch-execute cycle. They're the fastest type of memory and are really important for speeding up data access for the CPU. There's a few different types of registers. One of these is called the memory address register. This register holds the memory address of the data or instruction that's being fetched from or stored into memory. During the fetch stage, the memory address register holds the address of the instruction that needs to be fetched. Next is the memory data register. This holds the actual data or instruction that's been fetched from memory or is ready to be written into memory. It acts as a go-between for the CPU and memory, holding the data during data transfer. Then we have the program counter. The program counter is a special register that keeps track of the memory address of the next instruction to be fetched. Each time the fetch stage happens, the program counter gets updated to point to the next instruction in memory. Finally, we have the accumulator. The accumulator is a register that stores the results of the arithmetic and logical operations while they're happening. It holds the output of ALU operations and is used for further processing or for storing the final result. These registers are key parts of the von Neumann architecture. The von Neumann architecture is the blueprint for how modern computers are structured. It's named after the famous mathematician and computer scientist John von Neumann, who was one of the pioneers of modern computer science. The main parts of the von Neumann architecture are the CPU, memory, input-output devices, and bus. As we talked about before, the CPU is the heart of the von Neumann architecture. It's in charge of executing instructions and processing data. In the von Neumann architecture, there's a single memory system that stores both data and instructions. This means that data and program instructions are kept in the same place and they're accessed using memory addresses. The input and output, or I/O devices, are how the computer communicates with the outside world. They allow data to be put into the computer and output to be shown to users. For example, a keyboard is an input device, which allows us to send data to the computer, whereas a monitor is an output device, displaying data on the screen for the user to see. The bus is like a communication highway that allows data and instructions to be moved between the CPU, memory, and I/O devices. It's important to remember that while the CPU is responsible for executing instructions, it works within the larger von Neumann architecture. This architecture defines how the CPU interacts with memory, buses, and I/O devices to create a complete computer system.